Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. In this video, I would like to discuss on two subtopics of chapter 4. The first one is stability analysis via Bode diagram, and the second topic will be the transient response design via Bode diagram. In the previous video, we have introduced to you the gain margin and phase margin term. So what is gain margin and phase margin? Okay, gain margin is refers to the amount of gain which can be increased or decreased without making the system unstable, and it is usually expressed in unit decibel dB, while phase margin refers to the amount of phase which can be increased or decreased without making the system unstable, and the unit is normally expressed in degree. So stable system will have positive gain margin and phase margin, while the unstable system will have negative gain margin and phase margin. Gain margin is normally denoted by GM, and the phase margin is normally denoted by PM or VM. In this slide, I would like to demonstrate how to obtain the GM and PM value from a given Bode diagram. To obtain the gain margin, we have to find the frequency where the phase plot cross minus 180 degree line. So this is the intersection, and the frequency is called as omega, phase crossover frequency. And this frequency is normally denoted with these two notation. Either it is omega PCO or omega gain margin. Okay, to calculate the gain margin at that frequency, go to the magnitude plot and read the magnitude value at that particular frequency. And the value that you obtain at that frequency, substitute into the gain margin formula. So the gain margin formula is GM equals to 0 minus magnitude at omega PCO. Okay, and if you get a value below 0 dB line, then you should get your gain margin to be positive, and if you get a value above 0 dB line, you will get negative gain margin. Okay, now let us look at how to obtain the phase margin. Okay, to obtain the phase margin, you look at the intersection of the gain plot with the 0 dB line. So here, the intersection is obtained at this frequency. Okay, so this frequency is what we call as gain crossover frequency, and the notation used will be omega GCO or omega phase margin. Okay, so at this frequency, you go to the phase plot and then check the phase value. And then the value that you obtain here, you substitute into the phase margin formula, where the phase margin formula is PM equals to phase at omega GCO minus 180 degree. So if you get a value above minus 180 degree line, then you will get positive phase margin, and if you get a value below minus 180 degree line, you should get negative phase margin. Let us look at an example. So I have plotted a Bode diagram for a system where the black line is the magnitude plot and the blue line is the phase plot. Okay, first let us determine the gain margin value. So to determine the gain margin value, let us look at the phase plot. So the blue line is the phase plot. So here the phase plot cross 100 minus 180 degree line. So this will be your omega PCO or omega GM. Okay, so go to the magnitude plot and then read the magnitude value at that frequency. So you will get 20 minus 28, approximately minus 28. So substitute into the gain margin value with gain margin formula, which is 0 minus minus 28. Then you will get 28 dB gain margin. And for the phase margin, you go to the magnitude plot and find the frequency when the magnitude plot cross 0 dB line, and this frequency is what we call as omega GCO. And then go to the phase plot and read the phase value, and it is approximately at minus 125. So the phase margin is equals to minus 125 minus minus 180 degree equals to 55 degree. Thus, the system is stable. In this slide, I would like to demonstrate the effect of system gain K on GM and PM value. So I have plotted three magnitude plot for three different value of K, K1, K2 and K3. K1 is the K value that I have used in the previous slide. So from that, we have seen that the gain margin is equals to 28 and the phase margin is equals to 55. Okay, if we consider a K value greater than K1, you will find that the magnitude will raise by a certain value of K. So the magnitude plot is plotted as in the green color. So if you check the gain margin and the phase margin, you will get the gain margin to be 16 dB and the phase margin to be negative 36. And if you use another K value, K3, which is less than K1, then you will find that the gain margin will be 72 and the phase margin will be 90 degree. So from here, we can see that as K decrease, GM and PM will increase and producing a more stable system, while if you increase the value of K, GM and PM will decrease, thus producing less stable system. In this slide, I would like to demonstrate on how to obtain GM and PM using Bode diagram plotted using MATLAB. If you plot your Bode diagram using MATLAB, your plot will be slightly different than the Bode diagram you sketch manually. Okay, Bode diagram that you plot using MATLAB, it will split your magnitude plot and phase plot into two plots. The top plot is your magnitude plot and the bottom plot is your phase plot. Okay, to determine the gain margin, so as usual, you go to your phase plot and look for omega PCO, which is the frequency when the phase plot cross minus 180 degree. Okay, so and then go to the magnitude plot and then read the magnitude value, which is approximately minus 56 dB, and substitute into your GM equation, you will get your GM to be 56 dB. And to determine the phase margin, go to the magnitude plot and find the omega GCO, which is the frequency when the magnitude plot across 0 dB line. and then go down to your phase plot and read the phase value at that frequency. It is approximately minus 93 degree. So substitute that into your phase margin formula. You will get your phase margin to be 87 degree. So we have completed on how to determine the gain margin and phase margin from Bode diagram, and from that gain margin and the phase margin value you can determine whether your system is stable or unstable. So now let's proceed to the next subtopic, which is the transient response design via Bode diagram. Let us consider this example. So for a given control system shown in the block diagram, we have to find the K value that yield 9.5% overshoot in the transient response of a step input, and we will need to use Bode diagram method. So from this example, we can see that we can actually obtain the desired percentage overshoot using Bode diagram. To relate the transient response parameter, which is in this case is percentage overshoot, with the Bode diagram parameter, which is a phase margin, we need these two equations. So the first equation will convert from the given percentage overshoot into a damping ratio value, and then the second equation will give the phase margin value from the damping ratio value. So these two equations will be used in the example. So the first step is to sketch the Bode diagram for a convenience K value. So to ease our discussion, I have plot the Bode diagram for the given system using MATLAB, and I plot the Bode diagram for K equals to 1. Okay, so if you want to do this example on your own, you must plot it either manually or you can use MATLAB. Okay, then the second equation, you calculate the desired PM from desired percentage overshoot. So from the equation, the desired percentage overshoot is 9.5, and if you use the equation shown in the previous slide, you will get damping ratio to be 0.6 and the PM to be 59.2 degree. Okay. And then step 3, we have to find the frequency omega GCO or omega PM on the Bode phase diagram that yield the desired phase margin. So from step 2, we know that the desired PM is 59.2. So at your phase plot, find the frequency where you can get your PM to be 59.2. So using the phase margin formula, if you want your phase margin to be 59.2, then your phase value at that frequency must be minus 120.8 degree. So draw a line at that phase, and you will get the frequency to be at 14.8 radian per second. Okay, so this will be the frequency that we want to find in step 3. Because at this frequency, you will get your PM to be 59.2. Okay, now step 4, you at the frequency of 14.8 radian per second, go to the magnitude plot and read the magnitude value which is here is approximately minus 55 dB. So for this frequency to be your gain crossover frequency or phase margin frequency, this must cross at 0 dB line, meaning that you have to raise your magnetic plot by 55 dB. Okay. Okay, so to obtain phase margin 59.2, you have to raise your magnetic plot by 55 dB. Okay. To calculate the K value that will yield percentage overshoot of 9.5 degree, so we will use this formula. So this formula is actually the difference between the new magnetic plot with the old magnetic plot. So it is 20 log K new over 36 minus 20 log K old over 36 mass equals to 55. The amount of we raise the magnetic plot, and the formula K over 36 is coming from the normalized gain that we have performed if we want to sketch the Bode plot manually. Okay, so substitute the K old to be 1 because I plot the magnitude plot using K equals to 1, and you should get K new equals to 562. Okay, this is how you can actually design your transient response using Bode diagram. So that's all for this video. Thank you very much.